Hi guys, Miss O'Connell here. Let's give this do now a try. So why do objects vibrate in simple harmonic motion? If you can recall this from memory, that is wonderful. If you cannot, you want to head back to your introduction to vibration notes, where we defined what a vibration is, why objects vibrate, and how to measure those vibrations. You want to head back to those notes and refresh your memory. So pause the video and answer this question. Okay. So why do objects vibrate? Okay, so a vibration we defined as an up and down movement about an equilibrium position. Repeated vibrations or oscillations is considered simple harmonic motion. Objects vibrate or move with simple harmonic motion due to a restoring force. We analyze that restoring force using a ruler lined up on a table with one hand securing the end and the other applying a force to displace the other end of the ruler. Okay, we noted, and we wrote this down in our notes, that the displacement of the actual object and the force are opposite in direction. Okay, they increase proportionally, right? As the displacement increased on the ruler, the larger the force that was felt by the secure hand. Okay, and we said that that force can vary with time. So the answer to this do now, why do objects vibrate in simple harmonic motion? They vibrate due to a restoring force that is nearly proportional to the displacement of the object and points in the opposite direction. Okay, so we're going to talk a little bit more about what that restoring force is, how we measure it. And we're going to start by investigating the restoring force in a spring mass system. Okay, so we're going to try this out. You're going to click on the link that's in Google Classroom. It'll take you to the PHET, P-H-E-T, Hooke's law simulation. You're going to check spring force, displacement, equilibrium position, values, and one spring. Okay, you want to observe what happens to the magnitude and direction of the spring force when the applied force increases, decreases, okay, and then technically decreases even more. So the magnitude increases, but the direction becomes negative. Okay, so head into Classroom, open up that link, pause this video. Once the link is open, you can unpause the video and listen to the audio. Okay, so you should now have the Hooke's law simulation lab open on your screen. Gonna click intro. We want spring force, displacement, equilibrium position, and values checked. Make sure you have the one spring selected. We're gonna take applied force and we're gonna move it to 56 newtons. Note the direction and the magnitude of the spring force, which is the value labeled above the blue arrow or the blue vector. That vector represents the restoring force or the spring force. So an applied force is positive 56 newtons. The spring force is 56 newtons to the left, right? Left means negative. If we decrease the applied force to 7 newtons, we see that the spring force also decreases to 7 newtons, but again points to the left. Okay, if you toggle on the applied force, you will see that the applied force and the spring force point in opposite directions. Anyone think they understand why? Okay, so the force applied and the spring force here are Newton's third law force pairs, right? The force of the spring on the mass and the force of the mass on the spring are equal in magnitude and opposite in direction. Okay, let's change the applied force one more time. So let's take it on the scale and we're going to move it to negative, let's say negative 53 newtons. When the applied force is negative, the spring force is positive. It's 53 newtons, pointing to the right. Another thing that we can notice, so we can move it back to 7, and then back to positive 56, notice that the spring force, also known as the restoring force, always points towards the equilibrium line. So that's where it gets its name from. It wants to restore the object back to equilibrium. So that force is always going to point back towards the equilibrium position. Okay, next thing that we'll take a look at, which I'm going to have you guys watch the video and watch my screen. So make sure you're back on the video. Okay, so our observation here is that the spring force, aka the restoring force, is equal in magnitude but opposite in direction to the force applied. Right? This is because the force applied and the spring force or the restoring force are Newton's third law force pairs, meaning they have the same magnitude of force but act in opposite directions. Okay, another thing that we noticed here is that the spring force always points back towards the equilibrium position. Okay, make sure we write that down in our notes. Next thing that we kind of want to look at is the displacement. So that green arrow represents the displacement vector. Let's notice how the displacement vector changes in magnitude or direction when we change the spring force. So we're going to do the same thing, but this time we're concentrating on the displacement vector. So you can actually watch the video, and I'm going to show you this. So as you're watching, think about the displacement vector and how it changes. So I'm going to start back at positive 56 newtons. We have a displacement of 0.28, positive, right, because it points to the right. When we decrease the applied force to 7, our displacement decreases to 0.03 meters, but still positive. Okay, so when it's 56, restoring force is negative, displacement is positive. When we decrease the restoring force or the spring force, the displacement also decreases, but they are still in opposite directions. When the direction of the spring force changes, the direction of the displacement vector also changes. Okay, so as spring force increases, displacement increases. As spring force decreases, displacement decreases. We also notice that spring force and displacement, those vectors always point in opposite directions. So let's summarize here. The displacement aka the stretching distance, okay, of the spring, is equal in magnitude but opposite in direction to the spring force. Okay, and they are about proportional. Right? An increase in one means an increase in the other. A decrease in one results in a decrease in the other, but just in opposite directions. So please pause the video and make sure what you have, what is written on the screen in black, is written down in your notes. Okay, so now we have a little bit of better understanding about what this force is. So we know that the displacement is proportional to this restoring force, that the displacement of the object is inverse in direction compared to the spring force. Okay, the law in which describes this phenomena is called Hooke's law. Okay, so in the 1600s, Robert Hooke determined what makes an object elastic. Okay, elastic technically means that after a force is applied, the object can maintain its shape. Right? So in elastic collisions, the captions here just put the wrong word. Inelastic, there we go. In elastic collisions, oh, I did it again. You guys know what I'm saying. In an elastic collision, when the objects bounce apart, they maintain their shape. Okay, that's the definition of an elastic collision, right? If they don't maintain their shape, it's not a perfectly elastic collision. So elasticity is the ability of an object to maintain its shape even when a force is applied. Hooke determined with a spring scale that the force applied is about proportional to the displacement, as long as the material is perfectly elastic, like a spring. Okay, so the relationship between the displacement, also known as the stretching distance of a spring, and the spring force, also known as the restoring force, can be described and modeled using his law. Okay, so he stated that when an object is acted upon by a force, it can be compressed, stretched, or bent. If, when the force is removed, the object returns to its original shape, it is said to be elastic. Hooke discovered that not only are certain materials, steel rods, bars, wires, springs, diving boards, rubber bands, elastic, but the stretch that they experience is directly proportional to the load or the force applied. So he came up with an equation to model this mathematically. Okay, and that equation is F sub S. So F stands for force, S stands for spring. The spring force is equal to negative K times X. Okay, so F sub S is the spring force. K is a spring constant, which we know is a measure of the stiffness or the strength of a spring. Larger K indicates a stiffer spring, smaller K indicates a smaller or softer spring constant. Okay, larger K values are more difficult to stretch. X is the displacement of the object from its equilibrium position. Okay, X equals 0 is the equilibrium position. Okay, so X is a stretch distance. A is amplitude. Amplitude and stretch distance are two different variables. The amplitude is how far, or maximum displacement, from equilibrium once the mass is already added. X is the displacement of the spring from its equilibrium position when we add the mass. Okay, we're going to demonstrate the difference in a few seconds using a simulation. Okay, so X is displacement of the object from its equilibrium position. You notice that negative sign in there, okay? That is in there to account for the fact that the force is always directly opposite to the displacement or the stretch of the spring. Okay, another way to think about it is that the restoring force always points back towards the equilibrium position, which is in the opposite direction to the displacement vector. Okay. So I'm going to use a simulation really quick to show you the difference here. So here, right, the spring is in equilibrium. Once we add a mass to the spring will stretch to some displacement, which here is 1.6 centimeters. So the stretch distance is 1.6 centimeters. In order for this system to vibrate, we would have to pull this mass down further and release it. The distance from this position to where we release it from would be the amplitude. The stretch distance is how much the spring stretches when you add a mass to it. Okay, so let's give an example a try. What is the spring constant of a spring that stretches what is the spring constant of a spring that stretches 15 centimeters when a 45 Newton force is applied? Okay, so let's take out the there. So we have a spring at rest, we add a mass to it. Okay, that mass applies a 45 Newton force to the spring. That force causes the spring to stretch by 15 centimeters. We need to determine the stiffness of the spring. We know that spring force, displacement, and spring constant are related due to Hooke's law. So F sub S is equal to negative K times X. Okay, we are told that the restoring force is 45 newtons and that the displacement is 15 centimeters. We know that displacement is always measured in meters, always. So we must convert centimeters to meters. So we're going to move the decimal place over 2 times and then plug in what we know. So the restoring force is 45 newtons. That's equal to negative K times 0.15 meters. Okay, so if if X is negative, the restoring force has to be positive and vice versa. So when we solve for K, we will always get a positive value because it's a constant. Okay, the negative sign is attached due to the direction of either the displacement or the force. Here, we notice that the force is pointing up, displacement is pointing down. Okay, so technically X is negative and the restoring force is positive. When we divide both sides by 0.15 meters, we find that K is equal to 300 newtons per meter. Okay, so we determine the stiffness of the spring using Hooke's law. What do I want you guys to think about? We know that the mass, when it's applied to the spring, causes the spring to stretch, right? So the mass is responsible for that 45 Newton force. How could we determine the mass attached to the spring? So knowing the fact that the mass is applied to the spring and then it causes stretch, the force that is applied is 45 newtons. How could we find the mass? Any ideas? Let's start out by drawing a free body diagram for the mass. So think about the mass. What forces are acting on the mass? Okay, so we have the force that we can never escape, the force of gravity, and the spring force, right? So it's not technically a tension, it's the force of the spring. So previous to this point, we've called it a tension, but really in this situation, it's the force of the spring on the mass. Okay, the system is at rest once we add that mass. So when we add the mass, the system reaches a new equilibrium position. It remains at rest. The force of the spring is equal to the force of gravity, right? If all the forces are balanced, there's no acceleration, so they must be equal to each other. Okay, so just like we did in our force unit, right? We sum the forces and we set them equal to m times a. We use Newton's second law. The spring force points up, the force of gravity points down. Up is positive, down is negative. So the sum of the forces in the y, we have spring force minus the force of gravity is equal to 0. Okay, the mass is not accelerating. So if we add the force of gravity to both sides, we determine that that spring force, that 45 Newton force, is equal to the force of gravity that acts on the mass. We know that force of gravity, also known as the weight of an object, is equal to the mass times gravity, m times g. Yes, I know, unfortunately this stuff does build on itself and never goes away. So hopefully we still have this down from our force unit. Force of gravity is the mass times gravity. So we know that that 45 Newton force is going to be equal to m times the acceleration due to gravity on Earth, which is 9.8 meters per second squared. When we divide both sides by 9.8, we find that the mass would be 4.59 kilograms. Okay, so full circle here. We have restoring force from the introduction of vibrations. We now have an equation to model it, and we have connected it to Newton's second law so that we can find out more information about the system if we need to. Okay, so your job by the end of the day Wednesday, okay, is we're going to confirm this using a simulation, one that I've already sort of showed you. Okay, so in Google Classroom, you're going to use the link that's called the verification of Hooke's law. You'll follow the directions provided in the simulation. You'll screenshot Command-Shift-4 the results and attach the screenshot to the assignment in Classroom. This will most likely take you 5 to 10 minutes to do, so much shorter than a typical lab. Okay, but it's important to note the graph that is created. Okay, we're going to be applying this in a little bit more depth as we move forward. Okay, so you'll go to Google Classroom. You'll click on the link. It's called verification. You'll add the masses to the spring, and you'll type in the new equilibrium position in centimeters. So we have 1.5 centimeters. To change out the mass, you simply click. It'll change out the mass and meet its new equilibrium position, which you will then record. The instructions will pop up, okay, when you click instructions. Also, when you're done recording your data, you're going to click plot. It's going to create a graph for you. You'll Command-Shift-4 screenshot your completed table and graph and attach it to Classroom. All right, have a nice day.